Good morning everyone, and welcome back to our video series on the Mentor EM eddy current flaw detector. Today I'd like to share with you an application that's very well suited to the Mentor EM. It's an aerospace test, and it's the inspection of the bead seat area of aluminum aircraft wheels. And the picture here, I have a nose wheel from, I believe it's an Embraer. The wheel's been split in half, and we have it laying out on the bench top. And also in the picture is a purpose-built probe made especially for this application. It's a differential bridge probe, 2 coils. Each coil has its own microdot connection. The coils are rectangular in shape, and they follow the curved area of this bead seat on the wheel. So let's start out by taking a quick look in Mentor Create. Look at the setup we're going to use to work with this probe and inspect the wheel. The probe with aluminum works very nicely at a frequency of 175 kilohertz. Good starting point. The individual procedures that come with your aircraft or your wheels may specify frequency to be used in setup. Again, we chose 175 here. It gives a very nice response using the probe that we're going to use today. The coils are fairly large. We like to deliver lots of energy to them, so we're going to choose the maximum drive voltage of 16 volts. When we're driving the coils that hard, we usually select a little lower receiver gain. The default, I believe, is 22 or 28 dB. We're going to drop down to 16 for this application. We've chosen bridge 50, 50 ohm impedance differential to go with this probe. If we look at the panel setup, I've placed a reference. This is a static image, screenshot of signal response from the notch in our standard. We'll look at that in a moment. I have one Lissajous display, an impedance plane display, and I placed a strip chart here, and I'll show you why, as we get into the application itself, why having a strip chart on this application is very, very useful. So that's our app. It's a very simple app. Like I say, just a reference echo, a Lissajous strip chart. A couple of the other channel settings that we selected. This application, we're using a large coil to find a very small defect. The defect's only a couple of millimeters long. Coils are quite large. We need a good bit of gain to be able to see the standard notch. So again, drive voltage of 16, a little lower receiver gain. By default, we have our filters turned off. We're going to use no high-pass filter, and as we get looking at the signal, we may choose to use a little bit of low-pass filter to give ourselves a cleaner trace. Okay, so if we switch over to our view of what's going on in the bench, you can see in the live feed, I have a standard here. It's made from about an eighth or a quarter of a section of wheel itself. And right here in the wheel, I have a tiny little notch. I believe that thing is 3 millimeters long and fairly shallow. I have one of our purpose-built probes, and you can see this probe has a bit of a radius to it this way as well as this way. It's made to fit very neatly in that bead seat and slide along without needing a whole lot of effort to hold the thing in place. I have a bead seat application in the upper left corner here. So we'll launch the app. Okay, and just as we saw in Create, we have the reference in the upper left. We have the Lissajous, the strip chart. So I'm going to put the probe on a clean area of the wheel. First thing I'm going to do is balance. Okay. Now as I slide, one thing you should notice is if the probe moves around out of the bead seat area, you tend to get a lot of liftoff and wobble indication. There I'm just moving the probe back and forth over the bead seat area, and like I say, I'm getting quite a bit of probe wobble. So if I balance, we'll clear, balance, we'll clear the data. Now as I slide the probe over the notch, getting some jumps. I believe I have some cable issues here. Okay. Slide back over the notch. Okay, so now I'm going to pause, hit the freeze button, pause my strip chart, and you notice I've got a signal that sort of wanders all over the place as the probe changes contact with the bead seat area. I tend to get a fair amount of probe wobble and so on. When I look at this on the strip chart though, a couple of things jump out at me. These very fast vertical responses on the strip chart right here, here, and here come from going over that small notch. All right, so now if I open my overview strip chart and I place cursors down and select just the indication, and I can use pinch gestures to zoom in. So as we saw in one of the earlier videos, there are a number of gestures that you can use to interact with the strip chart. A pinch along this way will tend to zoom in tighter. It brings the cursors closer together and we examine a smaller part of the strip in time. If I pinch together, it has the effect of moving those cursors further apart. I can take my finger and swipe from side to side, and you see how that moves the strip right and left. So I can zoom in on just the crack indication, and you notice how much that looks like our reference echo. In fact, it looks identical to it. If we select one of these others, and we notice that the indication isn't very well centered up in the Lissajous. Again, that comes because of the probe wobble. I didn't have the probe as neatly in the bead seat as I could possibly have when I went over the notch. However, what I can do as a video balance now, if I come up to the Lissajous and double tap, that triggers what's called a video balance. So the instrument will look at all of the data points that are in the selected area. So all of the data points in the Lissajous, it takes the average of the X and Y position for all of the data points, and it figures out what offset to apply to move that image to the center of the screen. So if I come over here and look at this indication, again, it's pretty well off to one side. It's off in the upper left corner. If I want to get that down where I can look at it and properly size it, again, double tap, and the instrument calculates how to move that part of the indication to the center. If I want to get back to where I was originally, I simply select the entire buffer, do that average, clear, and when I select again, I'm back a little bit off center. So the nice thing about this, now I have the scan buffer set to 30 seconds here. You may not need a buffer that long, 10 seconds. When you're working just with the standard like this, it's only a small section of the wheel. That's a very long buffer. If you come into the display menu of the strip chart, that's where you can set the length of time for the strip chart to record. So if we drop that back to 10 seconds, put our probe on, we're going to do a balance, run across the and we'll pause. Now you notice at this point we have gotten quite a bit of it off screen. Select that whole area. Video balance. Move the whole mess back to the center. And we'll zoom in just on one of these quick vertical responses that we talked about. Center it up. There is one indication from the notch. I see another one out here. If I come out here, again, double tap, move it back to center. The line's looking a little bit raggedy, so if I want to clean that up some, I come down here and turn filters on at 100 Hertz low pass, and there's a very nice clean response. Okay. You can also use a little bit of high pass filter to try to keep the indication centered up. That tends to distort the signal a little bit. So I found using the combination of the strip chart to pick out the indications very quickly and the video centering, it really gives you a lot of capabilities to quickly scan the wheel and then come back and analyze at your leisure. Trying to just have a wheel, typically if you have an entire wheel, it's going to be in sort of that aspect. It'll be sitting face down on the bench. I have seen a couple of shops that have built very handy jigs using sort of a spindle and a wheel bearing that you can just drop the wheel down onto that spindle assembly, and it's held and on a bearing so that you can spin the wheel on that assembly while holding the probe. So rather than trying to move the probe across the wheel, which also works, you can hold the probe still, spin the wheel on the spindle, makes for a quick way to acquire the signal. Now, with a typical eddy current instrument, you're looking just at the Lissajous, and let's look at this one more time. As we run the probe over the wheel, we see a lot of movement in the signal. And you'll see the characteristic response from going across the notch. Right there's the notch. That jumps out at you, but you have to be looking at that Lissajous display all the time while you're scanning. It's much more convenient on the Mentor when you can hit clear, start, scan along, concentrate on keeping your hands on the wheel and on the probe and so on. Do a complete rotation of the wheel, pause. Now you can come back to the instrument, look at your indications, and you see, oh, right there is one of those quick vertical responses that I see in the strip chart. Center it up on the display. Okay, now I can compare the amplitude of that to the notch from my standard and get an idea of how large that notch was, how deep the crack is, that sort of thing. So that's our Beadseat application. Again, we have purpose-built probes for this that are made to fit the radius of the wheel and the radius of the Beadseat and the other dimension. The Beadseat application. Very powerful analysis capabilities on the Mentor EM with the ability to record, playback, and analyze individual sections, individual places in time along the rotation of the wheel, and the ability to do the video centering. So as the signal drifts off of the Lissajous, you can select something of interest, bring it back into view, do your analysis. So with that, I'm Dan Groninger. Thank you for joining me today. And please choose GE Inspection Technologies for your next application. Thank you.